Welcome to lesson 115. Today we're talking about symmetry, and specifically we'll get to that. All right, so here we go. Task 1. Here's a segment AB. Great. All right, it says if I translate segment up 5 units, then down 5 units, it looks the same as it did originally. Okay, so when I translate things, I need a segment to work with a vector, right? So I'm just going to go like this. And it says translate it up and then back down again. Okay, so let's try that. Oops, that's not it. I want translate by vector. I'm going to translate this object. I'm going to start with this point, and then I'm going to go up just to the end of this. And there we go. It's been translated up, right? It got slid up in the same direction as my vector. And then I'm going to do the same thing, translate by vector, but I'm going to translate it downwards, starting up here and going down to there. And surprise, surprise, it lands on the same spot. Are we shocked? No, not really. But check this out. It doesn't matter how I change my vector, because I'm basically just reversing my process, right? I slide it over that way, slide it back, right? I slide it upwards, slide it back down. I slide it downwards, slide it back up. I'm still going to end up back on my original spot. And you'll notice that although this one moves, my B double prime and A double prime don't move. Cool. All right. Question. What other rigid transformations can create an image that fits exactly over the original segment? Okay, well, we tried translation because that's what it told us to do. So let me get rid of that. How about reflection? So in order to reflect something, we need a line to reflect it across. So I'm going to just pop a line on here. There we go. And we will reflect this across this line. And we get a reflection. Move my graphics view again. There we go. And then I will reflect this back across this line. And where's it going to end up? Well, surprise, surprise, it ends up back where we started. And it doesn't matter where I change this mirror to, where the mirror is, it's still going to end up back where it started. Okay, cool. Awesome. So now let's try. All right, so we did a translation and we did a reflection. So let's try. What else we got? Well, we could try a rotation. So let's try a rotation. And for a rotation, we're going to need a point. So I'm going to just put a point there, and I'm going to use that as my center of rotation. Here we go. I'm going to rotate this object around this point. I'm not going to bother to change up this angle here, and I'm going to stick with counterclockwise because they already gave it to us. Boom. Okay, so it rotated 45 degrees clockwise. It used this as my center. Notice that if I move this around, it changes where it ends up, right? But if I rotate around point, I'm going to rotate my image around the same point, and instead of going counterclockwise this time, I'm going to switch the direction to clockwise. It ends up back where it started. That shouldn't be a surprise. And again, if I move this point around, the image in between moves, but not the final image, right? Okay, awesome. So now let's take a look at this. It says, here's one thing that I want to try. Now, in each of my cases here that we tried this, we just kind of like did a transformation and then we did the reverse of that transformation. I'm wondering if there's a two-step process that we can do where we can still end up back where we started, but we use two different types of transformations, two different types of rigid transformations. So we already did, reflect it this way, reflect it back. We did translate it that way, translate it back. We did rotate it this way, rotate it back. So let's try and mix them up a little bit. What ones do you think we could try to use, and what do you think would work? Well, I'm going to suggest that we use a reflection first. So we're going to reflect this across this line. We're going to get that. And then I think we might be able to rotate this back. So I'm going to rotate this using this point right here. I'm going to rotate it back. I don't know. I'm going to guess that it's like 95 degrees or something like that. Oops, I accidentally did it the wrong way. So let's try and do it again. So we got this, and we'll just set it at 90 degrees. Even though it's not quite going to be right. And we'll go clockwise. There we go. All right, so this made it back. All right, so let's see if it didn't land perfectly, but let's see if we could kind of like get it closer to where it maybe needed to be. Let's see here. So if I put this, how can I get this to line up? That's looking good. There we go. So theoretically, we could kind of like get things to land perfectly using two different types of rigid transformations. All right, so kind of cool. All right, so that was 3 possible answers for task number 2. Let's look at task number 3. Are there any single rigid motions that do the same thing? So in other words, instead of a 2-step process, can we get this thing to land on itself? Okay, and how do we do that? Well, let's think. Well, how about, if we could somehow find the midpoint of this, right, of this line segment, I think that we could rotate it around that point 180 degrees, and that would get us right there. Okay, now obviously I didn't manage to pick the exact center, but if I had, it would have landed perfectly, and that would be 1 step. Okay, awesome. So that's one way. All right. And notice the A ended up there. Couldn't we could also reflect then, right? Have A land on B and B land on A, right? So how do we do that? I think that if we had like the perpendicular bisector here and use this, maybe something like, I think that's probably close, right? We reflect this across this line. So this item reflected across this line. Boom. Okay, I didn't quite get it, but if I had lined that line up perfectly, it would have landed exactly where it was. Okay, good. So that's another possibility. What's another possibility that we could do? Well, if we think about this, we could actually reflect this using itself as the line of reflection, couldn't we? Right? Because this point is just going to reflect to where it is, right? If this is my mirror, if it's sitting on the mirror, it's already there, right? So let's try that. All right, we're going to reflect this item, and we're going to use this line as our line of reflection, and boom, it lands perfectly on itself. So that's 3 ways that we could do it, okay? Next, task 4, determine all the lines of symmetry for the shape your teacher assigns you. Okay, this is where I gave you guys this sheet here, and it's got a bunch of different shapes on it. Okay, so we're going to try and find a line of reflection that causes the shape to land back on itself. Okay, so looking at this shape, where would a line be that would allow this to reflect back onto itself, right? If I label here, let me label a couple of points here. We'll go like this. This is point A. B. This is point C. Oops. C. And point D. All right, there we go. All right, now I'm just going to grab these, move them around. This is point D. This is point C. This is point B, and this is point A, and now we can talk about this and know what we're talking about. Okay, so that line of reflection, well, it would be right down the middle, wouldn't it? So that line would look like this. So this point would be up here, this point would be down here somewhere, and let me actually make it so that we can see that line. That line is going to be red, I guess. Maybe make it purple. Purplish colored. There we go. And of course, it's going to be exactly where it would be exactly in the middle. And it would be a right angle. This right here would be a right angle. The other thing is that, let me see if I can use this. Maybe it's this one. Right, this right here has to be a right angle. Also, this distance right here and this distance right here would have to be totally equal to themselves. Because if you think about it, I'm going to flip A across. It's got to land perfectly on B if I flip it across this line here. Right? And same thing down here. D would have to land on C, and C would have to land on D. In order for that to work, this has to be a right angle right there. And right, these have to be the same length on either side. Right? There you go. Cool. Awesome. All right, so now let's look at well, let's do this one. Here we go. All right, so here, a rectangle that is not a square. Now, when we're talking about something that's not a square, the reason that we're saying that it's not a square is because all rectangles are actually, all squares are actually rectangles. And but not all rectangles are squares. Put that as D, and then we'll be able to move these guys around. Put D down here again. Here's C. Here's B. And here's A. All right. So as we look at this, right, where are our lines of reflection? Well, when we look at it, our lines of reflection, one of them is going to be right down the middle again, right? Right down the middle. Right between the midpoint of A and B and the midpoint of D and C. And I'm probably off by a little bit, but I think you guys have the idea. I don't know why this is not letting me. Oh, that's not what I want to do. Not letting me. I forgot what I was going to say. Okay, where's the other one? Well, there's another one this way, isn't there? So if I take this thing and duplicate it, oops, undo. I'm going to get another line. Yep, that one. So that one is going to go right here and right here. And again, we should notice that this intersects the edge of our shape at a right angle. Okay? It intersects the edge of our shape at a right angle. That's a right angle, and that's a right angle. And of course this down here and this down here, right? And again, this distance and this distance have to be the same. And this distance here, right, has to be the same as this distance up there. Okay? Right? Same distances. In order for A to land onto B, if we're reflecting using this line, and C to land on D if we're using this line. But if we're using this line here as our line of reflection, then A has to land on D and B has to land on C, so these distances have to be the same. One thing to keep in mind is that when we are doing a reflection, when points move, they always move exactly in a right angle, right, to the line of reflection. So from there to there, right, from C up to B, it travels in a travels in a line segment that is a right angle to our line of reflection. So here's our line of reflection running right through the middle, sideways. This, if I make a segment between B and C, which is this edge, that has to be a right angle. Okay, next shape. Let's look at a parallelogram that is not a rhombus. Okay, so if it is not a rhombus, that means that the sides are different lengths. Okay, so that means that this side here is different than that side there in terms of length. Okay, this side, because it's a parallelogram, this side and that side are the same length, and this side and that side are the same length. Okay, let me boost up my size of the pen that I'm drawing with. See if this works. Okay, so let's try a couple of things. Let's see if we can find a line of reflection for this. Well, if we do it straight up and down, like, something like this, then we can see that even if this was going to make it over to there and land perfectly, which it doesn't look like it would, I would have to put this right halfway between, then this is not going to land over there because that doesn't match. That distance does not match. Okay, so what about if I draw diagonally? Right, if I draw diagonally this way and get it perfectly down the middle, well, let's see. Remember that my points have to travel at a right angle. So if I'm going with this point here, it's going to travel at a right angle to my line of reflection, and that is going to be somewhere over here, and that doesn't land on this corner or that corner. So it's not a winning situation. It's not a winning situation. Okay? So a parallelogram that is not a rhombus has no lines of reflection. Okay? Oops. Let me do that. Let me go back one. There we go. So one of the things that I want to talk about this has no lines of symmetry. All right. So when we're talking about symmetry, let me get back to my selection thing. There we go. There are no lines of symmetry here on this shape. All right. A line of symmetry is a line of reflection that when you use it as a line of reflection, your object lands perfectly onto itself. Sort of like our first example here, a line of reflection that causes this to land perfectly on itself, right? That would be a line of symmetry. A parallelogram that's not a rhombus does not have any. It doesn't have any lines of symmetry. All right, so now let's look at this one, a parallelogram that is a rhombus. Well, the closest thing that we had the last time was when we had our line of symmetry going from corner to corner, right? Now let me put some letters on here again. That'll be point A. Right, move that up. Give me that. Put that up here. This will be point A. Point B. Sorry about that, but there was a glitch here. Okay, so looking at the parallelogram that is a rhombus, you got two lines of symmetry here, corner to corner, right? Both directions. And remember, these are going to meet at a right angle, and this distance here between, let me put in an extra point here, just an extra little circle. I don't know what that is. All right, so I am just going to use that circle right there. So we'll use this center point here as our point. We'll call that, whatever, point X, right? The distance between A and X and between C and X, right? Those are going to be exactly the same. And the distance between B and X and D and X is also going to be the same in order for those points to land on each other when you flip them across those lines of reflection. Okay? All right. And then we went on to the triangle. Now the triangle has three lines of symmetry. The obvious one is a straight up and down. But also if we rotated our triangle around and put C at the top, this would be straight up and down, right? Notice that it goes from A down to a point that's halfway between B and C. Same thing here, right? From B down to a point or across to a point that's halfway between A and C, and from C across to halfway between A and B. This is a right angle. These lengths here and here are exactly the same. Here and here are exactly the same, and here are exactly the same in order for those points to land on each other when you reflect. So three lines of symmetry for the equilateral triangle. And then let's look at the pentagon. It has five lines of symmetry, right? One straight down the middle. Again, it meets the opposite side right in the middle and at a right angle. And all I have to do is go all the way around from point to point, from A to B, and then across, halfway between these two at a right angle, down to C, directly across, halfway between at a right angle, right? From to D, halfway, all the way across, halfway between A and B, and from E to directly across halfway between B and C, again, always meeting at a right angle. So there's five lines of symmetry on a pentagon. I think we did the square also. Well, let's look at the square, right? It has four lines of symmetry. Just like the rectangle, it has up and down and side to side, but it also has the same as the rhombus, the diagonal ones. Those also work, okay? And again, each time it's going to be at a right angle to something, right? All right, what about the circle? Well, the circle actually has an infinite number of lines of symmetry because we could just keep slicing this pizza until the pizza slices were super skinny, but we would just keep cutting it and cutting it and cutting it, and those would all be lines of symmetry. So an infinite number of lines of symmetry. All right, let's get back over to our questions. All right, so Kieran thinks, give an example of a shape that has, says what's true for all of the lines of symmetry. Look at all of these shapes the class explored and focus on those that had more than one line of symmetry. Okay, so if we look at these, right, the circle has a ton, right? Rhombus has two, that's two or more. That's two or more. That's two or more. That's two or more. And that's two or more. What do we notice about all the lines of symmetry? Well, looks to me like they all cross right in the middle. They all intersect at the same point. They all cross at the same spot, right? Definitely, right? Okay, and here, and for the circle, everything has to go perfectly through the middle. So yeah, it looks like they all cross at the same spot. Okay, that would be the answer to there. Give an example of a shape that has two or more lines of symmetry that do not intersect at the same point. Well, geez, I have no idea. I have not been able to think of one, right? If you can think of one, let me know. A shape that has two or more lines of symmetry and those do not intersect at the same point. Okay? All right. What would happen if you did a sequence of 2 different reflections across lines of symmetry for the shapes you explored in class? All right. Okay. 2 different reflections. Okay, so let's see. Let's try this one with the rhombus, right? If I use AC as my line of symmetry and I flip this stuff across, well, D will land on B and then B will land on D. But it's still going to look exactly the same. And then if I use BD as my line of symmetry, A is going to land on C and C is going to land on A, but it's still going to end up in this same sort of position. It's going to look the same on the page. Okay? All right, last question. Kieran thinks both diagonals of a kite are lines of symmetry. Now, a kite has a specific meaning in geometry. It has a very specific meaning in geometry. It is a shape that has two pairs of sides that are the same length, meaning this side here, AB and BD, is exactly the same length as each other, right? And then DC and AC are also the same length, okay? So not with like a parallelogram, if we bounce back over here, right, this side and this side are the same length, and this side and this side are the same length, but notice they're across from each other. If we look at a kite, the sides that are the same length are the ones that are next to each other. So anyway, let's go back to our question. Kieran, let's go back to our question over here. Yes. Kieran thinks that both diagonals of a kite are lines of symmetry. Okay, both of them. So that means this one and this one are lines of symmetry. Tyler says, only one of them is. The question is, who's right, Kieran or Tyler? Is only one of these a line of symmetry, or are both of them a line of symmetry? Or are they both wrong and neither one is a line of symmetry? Right? A line of symmetry is where if we reflect across that line, we still end up with the shape exactly in the same position and matching itself. All right, so that is that. That's the last question on 115. I think it's this one. Nope, this one. Right, that's the last question. Who's correct? And explain how you know. Explain how you know. Right? Be sure you do that part. Okay, great. That's it.